Okay. So I will begin showing a picture of Saltstraumen in northern Norway. And the reason for that is that we have calculated a similar strong current on the Norwegian shelf and in the shallower part of the North Sea during the Storegga tsunami. And Saltstraumen here is said to be one of the strongest tidal currents in the world. Mean velocity is 3 to 4 meters per second, with a maximum of 11 meters per second. And the first current that ran towards the back wall of the Storegga slide just after the slide was released had a maximum of 10 meters per second. And so we think that strong currents during the Storegga tsunami could move sediments on the shelf and also could trigger turbidites from the shelf break. Okay, I'm not alone on this study. Bjørg Risebrobakken and Tine Rasmussen, marine geologists working with foraminiferous, and Stephen Gibbons and Finn Løvald, they did the numerical simulations, and they should also be considered as co-authors of this presentation. So I will answer 3 questions during the presentation. And the first is, did the Storegga tsunami happen within the 8.2 cold period? And the next is, could the Storegga tsunami also influence the deeper seafloor sediments? And the third question, is the climate signal of the 8.2 event in marine sediment cores contaminated or could be confused by the Storegga tsunami? I will start first giving a little background about the Storegga tsunami. And here is the Storegga slide, a giant slide outside of Norway that triggered as a big tsunami. And we have been mapping deposits along the Norwegian coast, all the way from far south to north. It also been mapped in eastern part of Scotland, and also now there's new sites also here over in the western part here in Shetland and the Faroe Islands, and all the way there's indication all the way over here on Greenland of the tsunami. And on the right side here is the reconstructed run-up heights. That is to what elevations that we have found deposits. And we can see that the largest run-ups are in this area here closest to the slide. The best preserved deposits are found in lake basins, and here's a picture of such a lake basin. This is from the northern part of Shetland. This lake here is located a few meters above sea level. And in this area here, close to the outlet area of the lake, that's where we found much erosion and redeposition of material from a current that ran from the seaside of the lake into the outlet area of the lake basin. And here, I think this is the raft that we used for coring. And I also found another picture that I would like to share with you of the raft. And a few weeks ago, I showed this picture to my students, and they started laughing. And I can hardly recognize this guy here standing smiling on the raft, but this is actually me. And I think Jan is the photographer of this picture. So this is a 20-year-old picture of me. And students always like to see that our teacher is getting older. Well, anyway, based on all this work we did, we made a sedimentological model of the tsunami deposits. And this is a cross-section showing basin on the seafloor, and then here's a lake basin up here. And what happens when the tsunami would run into such a lake basin? And here we see the tsunami, how it flows into from the seaside of the basin. And we found much erosion, as I mentioned, in this part of the lakes, close to the outlet area. And a lot of material here is ripped up from the lake floor, bringing also in sand and gravel in this area. And as the water continued rising, we could also find sand. Well, this shows here sand and gravel deposited on the erosive surface. And also then we would have erosion further inland and upslope. And the next image here then shows what we call the backwash. And the backwash then carries material from the terrestrial environment into the ocean. And we have deposition here of terrestrial material also forming a tsunami deposit off the coast. And so one problem is that 90% or even more than 90% of the material is redeposited. And so it is difficult to radiocarbon date the event precisely because we have all this redeposited material. But in a few lakes, we found moss that we know were killed on the day the tsunami happened. And let's take a look at this beautiful, well-preserved moss stems that we found. And here is, this one here is a picture of part of the core showing the tsunami deposit. It's a mixture of different kinds of material. We have rip-up clasts of peat and mixed in with sand and different kind of organic material. And within the sand, we extracted these moss fragments shown here, for instance. They looked a little green when we uncovered them, and after we dried them, they looked even greener. And so we went along and we measured what the green color was from it, and it is chlorophyll, small amounts of chlorophyll that is still preserved in the plant fragments. And so we know that they must have been alive when the tsunami happened, and they were quickly buried in the tsunami deposits. And so then the radiocarbon clock started ticking, and so we were able to date the event much better than we had before. And here is a core showing the tsunami layer here in yellow. And in this part of the sediment, we found the green moss fragments that we could radiocarbon date. And so we ended up with a radiocarbon age of 7,300 plus minus 20 radiocarbon years. Okay, so in this picture here, I show three panels. And the first panel here is the calibration of this radiocarbon date of 7,300. And the green line here shows the original distribution of the calendar dates. And in green here is the simulated distribution when we also take account of the dates that we have below and above the tsunami layer. And so this line here shows the simulated distribution of the calibration of those ages. And below here in the C and D panel here is from the ice core record, the GRIP oxygen isotopes from the GRIP, and also here is from the GISP2, the methane record. And we see that the coldest part of here aligns on top of the age of the Storegga date. So actually we see that within the coldest decades of the 8.2 event seems to be the time of when the Storegga tsunami happens. Okay, now we have answered the first question. of the three, yes, the Storegga tsunami happened within the 8.2 cold period. Okay, let's take a look at the next question. And that was, could the currents in the Storegga tsunami influence the seafloor sediments? And I think that one thing that we have learned from tsunamis in the last years is about the backwash. I don't think we had much idea of the backwash, the return currents that goes back into the ocean. This is from the Indian Ocean tsunami in 2004. I think it shows this is from Thailand. And the thing is that most of the victims in a tsunami are never found because they are transported into the ocean with all the huge amounts of debris. And where is all this material deposited? It is deposited in the ocean. And so the backwash is, I think, more important than we thought of in starting working with tsunamis. And also, if we take a look at the Tohoku tsunami, the Tohoku tsunami that happened in Japan in 2011 was also very dramatic. And a large part of the Pacific was actually full of debris that floated around for several years after the tsunami. And this here shows some of the finds in Hawaii. They found a village sign from Japan. There was a rowing boat over here. The motorcycle was found within a container that floated on land here, fishing boat over here. And also there was a nice story about a football that was found in Alaska. And this football here belonged to a boy, a 16-year-old boy in Japan. And they found his name on this football. And he and his family lost everything in the tsunami, their home and all their belongings. And the only thing that he had left was this football that they returned to him from Alaska. They found his name on the ball, and also here the name of the school. So about the currents that are in a tsunami, for long waves such as the Storegga, the currents are uniform from the sea surface and all the way down to the seafloor. This is very different from a storm waves. So the flow velocity here, U, is a function of the surface elevation, the wave height of the water in the tsunami, the sea surface elevation, and divided by the depth of the water depth of the ocean. And so this should be multiplied by the square root of G times the water depth again. So the shallower it is, the higher the flow velocity, and also the higher sea surface elevation, the wave height in the tsunami also gives higher flow velocity, the occurrence in the tsunami. And so we can take one example. Say that we have a sea surface elevation of 5 meters and water depth is 250 meters. So that is the situation in many places along the Norwegian coast. We have the shelf around 250-meter water depth, and the tsunami was many places sea surface elevation more than 5 meters. And so we could put the numbers into this equation. And when we do that, and if we replace the G by 10 instead of 9.81 meter per second square, we get a simple expression here. We can take the square root of 2,500, and that is 50. If you remember math, and 50 times 5 is 250, and so we have 250 divided by 250, and we get 1 meter per second. And 1 meter per second current is a strong current that can move sediments on the seafloor. And so Also, you might remember this curve, Hjulström's diagram, relating flow speed to erosion, transportation, and deposition. And 1 meter per second here is 100 centimeters per second. And so I can put up a line here, and we can see that we can erode all the way from silt here, fine silt, and up to pebbles in such a current. Okay, let's take a look at the simulations that we did. And they are shown here. And so first of all, we have to look at the scale up here, showing the maximum velocity here within the tsunami from 0 to 5. So red here is 5 meters per second. And so any color that is darker than red, for instance, brown that we have over here, for instance, has a higher velocity than 5 meters per second. This is the maximum velocity during the whole tsunami simulation. And so, for instance, just to repeat what I said in the beginning, we have very strong currents from the shelf here going into the back wall part of the Storegga slide area. And this current here was about 10 meters per second. This is then about the maximum of Saltströmmen that I showed in the beginning. We got also very strong currents in the shallower part of the North Sea, around the Faroe Islands on the shallow area there, all along the shelf of the outside of the Norwegian coast here. And also interesting, if you go from, let's say you go from white down here to blue, like we do all the way down at the depth of 1,000 meter here, we have 1 meter per second of current velocity. Okay, let's take a look at the bigger picture. This is Norway here and Scotland here and the Faroe Islands and Shetland, but let's take a look at the bigger picture here. And here we recognize the Storegga slide is located here. We saw this image on the previous slide, and now we have zoomed out to see it in a bigger picture, bigger area. So Norway is here, Iceland is over here, and Greenland is here. And this shows the maximum sea surface elevation during the simulation time of the tsunami. And so we see that we have more than 2 meter elevation of the sea surface in a big area, a large part of this ocean between Norway and Iceland and Greenland. And also propagating into the Barents Sea here, we can see that we have also quite a high surface elevation of the tsunami. Let's compare the surface elevation if we involve also the depth and see what kind of currents this will give us for the same area. And here is what it looks like when we look at the currents. So now we have maximum velocity here goes from 0 and up to 0.5 meters per second. And anything that is darker than red is higher than that. So you see that all of this here around the Storegga slide and Norwegian coast and around the Faroe Islands and Iceland is much bigger than 0.5 meter per second. But I would like to point to the area here in the deeper part of the ocean. We have like 20 centimeters per second of maximum velocity. And that is actually large enough to move the very fine sand grains, for instance, of foraminiferous. But the stronger currents are restricted to the shallower areas. And so I think that the answer to the second question that I had here, that the Storegga tsunami could also influence the deeper ocean. Okay, now we shall look at some of the sediment cores. And we will spend most time looking at this core up here. It's called MD 95 2011 up here at a water depth of around 1,000 meter. And this core has recorded a strong and dramatic cooling during the 8.2 event. And we will look more carefully at those deposits that has been inferred to be this cold climate 8.2 signal. And we will also mention this core here, east of the Faroe Islands at a water depth of about 350 meters or so, Link 14, and also this core here, 2803 in the Norwegian Channel. But we will spend most of the time, because this is the core that we have focused on in this paper, that we reinvestigated this core here. First, we will see at the radiocarbon dates of this core. And those are shown here. We have depth on the x-axis, and we have calendar years on the y-axis. And we see a jump here in ages. So right here, there's a jump in radiocarbon ages across this boundary here. This here is at the depth of 535 centimeter. And this is immediately underneath the 8.2 layer. The sedimentation rate is fairly constant. It's about 20 years per centimeter. And the H model that we did is this red line here. And I will use this as our H model for the core. And so the next, we will focus in now on this part here of the core. It's about 1 meter long, and it covers from 7,000 to 9,000 calendar years before present. So it includes the 8.2 event. So I will show now 5 panels, and this is from the paper, but we will focus in on the 2 first ones. This is the A and B, and I will come back to C, D, and E on the next few slides. And so what we see here is the amount of sand grains within the layer is right here, and we have little more than 30% contains of particles, grains size bigger than 63 microns. And this is not typical, because most of the core here has 95% of the core is clay and silt. So this layer here is very different if we look at in terms of the grains that we find here. And we also have part of the grains are organic. Those are foraminiferous. The other is mineral grains. And so we also have mineral grains that are larger than 150 microns in the layer, like this increase here. So we have like 2,000 grains per gram of sediments that are larger than 150 microns. The next panel here shows the numbers per gram sediments of the planktic forams. And we have 2 planktic forams here. It is the Neogloboquadrina pachyderma. It's the cold polar water species. And we have the warm Atlantic water species, the Neogloboquadrina incompta. And we see that both are showing a dramatic increase. We have a very high increase in the cold water one, and also in the water one. And what we did then was to pick out the forams from the layer itself and radiocarbon those forams. And then we got ages that are 3,000 years older than what we should expect if this was the 8.2 layer. This one here was dated the cold water 11,400, almost into the Younger Dryas here for the oldest samples. So, but also the warm water species here are about 1,000 years too old than what we should expect. So this also indicates that the material here is redeposited. The next panel here shows the benthic species of benthic forams, and these here, they usually live on the shelf and not in the deeper water. So we have a peak here in this species here, and also in this one here that indicates that they must come from somewhere else than where they are found. So indicates also redeposition from the shelf to this area. And then we come to the oxygen isotopes, and this was used to reconstruct the temperature during the 8.2 event. And from that, for the heavy isotopes here, they found that the ocean surface was 3 degrees colder than today. And it's these high values here. But now we know that these are redeposited. And so when we look at the values here, they align more with the younger Dryas or very early Holocene values of the oxygen isotopes. So clearly we have resedimentation here of older material. And if we continue the line here that goes through the peak here, down to the finally the next panel here, that is the age of the Storegga moss, the green moss here. We see that it's fairly showing the same age as the calibration of the Storegga, the green moss of the Storegga event. Okay, so what can we say about this layer in this core that is called the 8.2 layer? And so unfortunately, we don't have any X-ray image of this core, and we don't have any detailed description of the sediments. And today, very little of the core is left. Most of it has been used for different analysis, but we can say something from the analysis that we have done. And so we know that it's a 2 centimeter thick layer from 533 to 535 centimeters. We know from the jump we had in radiocarbon years that the lower boundary is erosive. We have a hiatus here of 400 years. Yeah, maybe this would be about 20 centimeters of erosion of the sediments. And we also know that 30% of the grains are in the sand fraction, and we also have quite a large amount of grains that are larger than 150 microns of mineral grains. And these are the grains that were inferred to be dropped from icebergs in the 8.2 event. And also we know the layer is fining upwards. So this is what we can say about the sedimentology of the layer. But from the other, the 18O and the radiocarbon dates, we can also say something more. We have here an large increase of 4Ms, 12 to 14 times the increase just in this layer relative to the background values. And there's a mixture of polar and Atlantic species. And we also have benthic species that usually are found in shallower water on the shelf. The oxygen isotopes from the cold water forum indicate a cooling of 3 degrees. Well, we know that this must be wrong because it is from older periods, because we have radiocarbon dated these cold water forams, and they are much older, 3,000 years older than the 8.2 event. So our conclusion is that this has nothing to do with the 8.2 climate signal, but we think that this layer is a turbidite triggered from the Storegga tsunami, from material transported with the backwash out to the shelf break, and all this material is released on the shelf break and form a dense fluid that flows down the shelf, go past the core site and deposits at turbidite, bringing in the older sediments. Let's take a look at a similar layer they found in Japan, outside of Japan, after the Tohoku tsunami. And this is a nice, very nice, interesting publication from Japan. And they have nice data from sensors that are sitting on the seafloor during the tsunami event. And this sensor here is measuring pressure and also seismic waves and temperature. And these sensors here, they were influenced, they were covered in sediments, also in very deep water after the tsunami. So the first image here shows the tsunami running up the slope, running into Japan, and the backwash then is carrying sediments to the shelf, and we form a dense cloud of sediments, water filled with sediments, and this here starts to flow down the slope as a turbidity current. And this turbidity current, particular one of the sensors here, is lifted into the turbidity current and transported 1 kilometer down the slope inside the turbidity current. As it is recording pressure and temperature, it's a very interesting data set. And here you can see it is laying on the side here. And so what we know here is that the tsunami here produced turbidites on the coast on the slope of the outside of the shelf of Japan. And now I have a picture of one of the sensors. This sensor here is sitting at 1415 meter. The one that was moved 1 kilometer was sitting at 1,000-meter water depth. And you can see here what they show in this picture is that it is sitting in a fine-grained soft sediment layer, and this covered a wide area of the deep sea after the tsunami. So they say that this layer here is about 5 to 15 centimeter thick. Okay, so now I come to the conclusions, and we have answered the third question, that the climate signal of the 8.2 event in marine sediment cores could be contaminated by the Storegga tsunami, and we think that this core here indeed is contaminated by, and it's not a 8.2 layer, but it is a turbidite triggered by the tsunami. So that is one conclusion. And so this is actually the first identified Storegga tsunami turbidite, and it's not the 8.2 layer. So we also here over in the Faroe Islands, I haven't spoken much about this layer here, but this is a normal graded sand layer 4-5 centimeter thick. And this we think was deposited directly underneath the currents of the Storegga tsunami. So that is a sand layer here in outside of the Faroe Islands. And this core here in the Norwegian Channel show a rise in the cold water foraminifera, the planktonic Neogloboquadrina pachyderma at 8.2. The layer is 3-4 centimeter thick, but there's no sand in here. There's just clay-rich silt. And according to the simulations here, we have like 0.5 meter of current on the seafloor. So it should be strong enough to redeposit and contaminate the 8.2 layer here. So we cannot prove that this is also influenced. I think we should go back and look at the original data, the raw data. Unfortunately, that was never published, but that's worth doing, I think, to take a look at this 8.2 layer here. So, and this then is my final slide. I think the climate reconstruction of a large and abrupt 8.2 cooling event in the Nordic Seas is faulty and should be discarded. The reconstructions of a very cold sea surface and that the sand grains were deposited from icebergs are wrong. I also think that a large part of the seafloor between Norway, Iceland, and Greenland could be influenced from movement of sediments by the Storegga tsunami. It might actually be difficult to find a core site in this area that wouldn't be disturbed by the tsunami around 8.2. And it might also be worth looking at other sediment cores in the North Atlantic of the 8.2 event. For instance, Kiki Clive and another in 2008 and Elliott and others in 2006 could also contain redeposited forems. And I think a reinvestigation could be worth doing also here. Some of these, of course, they show very high sedimentation rates, and I mean that's a good thing. That's the thing we would like to see, high sedimentation rates, but the sediments has to come from someplace. So often high sedimentation rates mean redeposition. So that's why it is so important to look at the sedimentology of the layer and also to pick out the forems and try to radiocarbon date them, the same forems that you use to reconstruct the temperature and climate. And that is now possible to do because you only need small samples of about 100 forems to do a reliable radiocarbon measurement. So okay, I think that is the end of my presentation. So
okay,
thanks for listening.
Thank you so much. That was really great, Stein. That was very, very interesting. And we'll turn it over for questions. We'll start with the group in Norway, in Bergen. But while they're getting ready, perhaps I can ask you a couple of questions. I remember talking to Axel Timmerman about the 8.2 release of water through Hudson Strait into the North Atlantic. And if it was as catastrophic as people thought, that might also have created a tsunami. And I wondered if you have seen any or thought about any connection between the initiation of the Storegga slide and a massive disturbance from the west related to the release of water from Hudson Strait.
Yeah, I know people have been thinking about this. Could there be a connection? I mean, they sort of happen at the same time. There is so much water coming out that actually that will produce a tsunami in some way. But I don't see. I think that it's difficult to say whether they are connected. I think these two events might be just happening at the same time and not really connected. I think it's a typical thing for us humans to do is if something happens at the same time, we think that they must be connected in a way. It might not be the case. I don't see that there should be. I mean, you increase the sea level a little bit, and how could that, for instance, change any of the thing with the slide? That would be one idea, and I don't think that I haven't seen any good explanation, a connection there.
Is it possible to use the model, the simulation that you used with respect to that 8.2 release of water from Hudson Strait?
I don't know. I don't think so. This is the model here consists of two parts, and it's the slide that is moving down the slope and then producing the tsunami. And then it's the tsunami model looking at the water, how the tsunami is propagating. I'm sure there are other people simulating better the release of all this water through the Hudson Strait.
Okay. All right. Thank you. Let's turn it over to Andreas Born and Bergen.
Hello, my name is Eirik. I was just wondering, the sediment cores from the Nordic Seas in comparison to other climate records from ice cores have a bigger overestimation of this cooling event?
Yeah, it's a good question. I think the idea with the icebergs, for instance, that we with all the mineralogenic particles that is in the core at the Vering Plateau that I talked about, is more dramatic than what is than the signal in the ice cores would indicate. But again, the ice core is probably the archive that shows the best the 8.2 event. No, I cannot answer that question. Maybe someone else here could do that.
And then
Okay. Yeah, go ahead.
one last question, if that's okay.
Sure.
How do you think your findings can affect other paleoclimate studies that strongly relies on marine sediment cores?
Yeah, I think this shows that the thing that I have been missing with, not to say anything wrong with marine geologists, but sometimes I feel that they don't pay much attention to the sediments itself. They don't do much. They are very into looking at the foraminiferas that they find there, and they have often the idea of particles are just accumulating on the seafloor nicely and dropping nicely down. I think it is very important also to include the sedimentology of the sediments, and sometimes sometimes that's not done, I think, as well as it could be, because they miss this information that we like to think that our records are uniform and perfect, but often that's not the case, and we should be careful. And a good idea here is then to pick out the foraminiferous. If you're doing forams, for instance, pick them out and date them with the radiocarbon method to show that they are not redeposited.
Thank you.
Any other from your group in Bergen? No? Good. Any questions from Manchester? No? Okay. How about here? No questions here? Yes, Tom Johnson has a question for you.
That was a great talk, Stein. Thank you very much. I'm interested in the height of the tsunami. You gave an example of the tsunami being 5 meters high, which strikes me as out in the open ocean being way too high. That a tsunami would typically be on the order of perhaps 1 meter.
Mm-hmm.
So as you made your calculations of current speed on the sea floor, did you take all of this into account, or do you have some independent way of knowing what the height of that tsunami would have been in the deep sea?
No, it's a very good question, because usually a tsunami triggered from a subduction zone fault is much smaller in the open ocean. So we think that most tsunamis are less than 1 meter in the deeper part of the ocean. The 5 meter you were referring to is on the shelf, and that is much shallower than in the deeper ocean. So, but I showed you the picture here of 2 meters in the open ocean. That's surprising, I think, also. But the Storegga tsunami was a very big. It's different than a tsunami triggered from a subduction zone earthquake, because it is as the slide is moving down the slope, it is generating the tsunami, and so around the Storegga slide we will have very high surface elevation around the slide, and you can see on that image, sort of in the direction of the slide where the slide is heading. That's also in that direction we have the biggest wave.
Thank you.
I'll ask if anybody else has any questions, but can I also ask if did you in your map of where you found evidence for overwash along the coast, it didn't include Svalbard. I wondered if there's any evidence from Svalbard.
Yeah, I don't know. The simulation doesn't reach that far. So but as you could see on this, maybe I could take that up. That I don't know if we can find that. It's probably this one here.
One before that.
Is it? Do you see it? Okay.
Yeah.
Yeah. So we don't have Svalbard included here in this domain that we had available. So I don't know, but there is. Yeah, I haven't seen it. I've looked at it when been studying the sea level changes in around Svalbard, but I haven't seen any. I mean, you could think that the driftwood on Svalbard would be lifted up at that time, but I haven't seen any good indications of that. So it doesn't seem to have had any big impact.
Yeah. Okay. All right. Any other questions from the group at large? Okay, I don't see any. So with that, I'd just like to thank you so much for a fascinating talk. A lot of food for thought here. And I would recommend everybody to take a look at this paper that is on the web from Stein, and also his other papers that I'm sure are referenced, because they're all really great. So thanks again, Stein, and we'll put up the recording.
Well, thank you. Thank you very much.
Okay, take it easy. Bye-bye.